all inert, okay? So the material has still not reached its ignition temperature, so all the heating is inert. We're not talking about sources or sinks or anything like that. At this stage, everything is still inert. And in the case of the way in which Quintieri handles it, it doesn't really matter which path the heat follows. He's basically taking the heat contribution of the flame as being this particular term phi, and it doesn't he wouldn't care at all if it was from the gas phase or the solid phase. Okay? It doesn't really make any difference to his formulation because it's just going to be called phi. Okay? So that's the problem as simplified by Quintieri. Now, then comes reality. Okay? So then you have all sorts of other issues. So before we even address the problem of flame spread, you know, we have to start looking into an earlier problem, which is how are we going to find this ignition temperature? Okay? So if we don't understand ignition, then we cannot get into flame spread, so we need to take one step back and find this value of the ignition temperature. Okay? So we're facing a problem. Oops. So we're facing a problem of endless complexity. Okay? So here's a piece of wood, and the piece of wood is being heated by radiation. You're going to have convection, you know, your film coefficient. You know, you're going to have heat losses in the back. You're going to have water migrating. Normally the materials are heterogeneous, so you're going to have water concentration, for example, around the eye of the wood. And you're going to have different heat transfer and different mass transfer if you're against the grain or with the grain. You're going to have different chemical processes like glowing, for example, which is smoldering, and which is a solid phase combustion. So the problem in itself is incredibly complicated. Okay? And once again, you know, we need to take a step back and start looking at this problem in a much more simplified manner. Okay? And but we have to keep in mind exactly what we are assessing, so we cannot get lost in trying to figure out something that effectively becomes irrelevant. Okay? So many times one of the problems that we tend to have with very complex problems is that we know what we can solve mathematically. Okay? And what we do is we transform the problem to fit the math as opposed to actually create a math to solve a problem. And that way we end up solving problems that are not existent, just simply because we can actually solve the math. Okay? Now, it looks very pretty, you know, in a paper, but it's absolutely and utterly useless because you're solving a problem that is unreal. And this is one of those situations where you actually have an enormous risk of landing in that path. Okay? And we have to be extremely careful. Perfect example, you know, one of my former associates, who is a professor now in Imperial, developed this model of pyrolysis, you know, within the solid. And they were trying to predict how the material was going to gasify, but because they couldn't get a proper reduced chemical kinetic mechanism, the way they actually do it is by using genetic algorithms. In other words, they were fitting in a very sophisticated way the data. So they started with one chemical reaction, they moved to 2, they went to 3, they went to 4, they went to 5, you know, and they kept increasing the number of reactions, many parameters being involved. But of course, the genetic algorithms will always find you a number. Okay? So 2 years ago, it was quite interesting. He was giving a presentation in Lund, and basically he was assessing, you know, these pyrolysis models for, I think it was a plastic, a PMMA. And so he was assessing the pyrolysis models only to come up to the conclusion that the chemistry was irrelevant. Okay? So effectively, you've launched yourself in a certain path to try to solve a problem, and you start creating a mathematical problem because you can solve it, and forgetting completely what you are assessing. And this is a perfect case where we have the risk of doing that. Okay? Ignition is going to define the onset of the fire, and that's what we're interested in. We want to know when the fire starts. Now, the path that it follows is going to be very complex, and we have to be able to simplify it in a way that we can actually achieve the objective. Okay? So ignition is going to control flame spread, and therefore is going to control fire growth, is the VS in the system. Okay? So we need to be careful. Now, if we look at the problem in its complexity, that's the way it looks. So effectively, if I take a piece of wood and I start heating it up, it's going to start degrading, it's going to crack. So you're going to have an area of cracks. Basically, you're going to have areas where the material is going to be consumed, and you're going to get a porous environment being formed. So you have all those holes in here. So the charring region, or this area that is degraded, is going to progress with a certain velocity. Okay? And that velocity is going to be preceded by a pyrolysis front, because there are multiple reactions that can actually happen in here. And there's going to be a thermal front that is going to be here, and there could also be an evaporation front at some point. In the same time, oxygen can actually diffuse to the inside of the material, while fuel can actually migrate to the outside of the material. And in the process, they can react, and you can actually have oxidative reactions like glowing, for example. Okay? So you can have all sorts of things going on. You're going to have re-radiation coming out. So you can complicate this problem, in as much as you want. Okay? Now, at the end, we're going to be looking into integral parameters to try to get an estimate of what is going to be the heat transfer through this complex system. We're going to have to try to get an estimate of the boundary conditions, both at the front, the back, and the edges. Okay? And we have to find a way by which we have to establish how the material is degrading. Okay? That's what we need to do. So, and how are we going to assess that? By means of the ignition delay time. Okay? Now, why the ignition delay time? Okay, it says it there. It's an observable event. Okay? So the magic of the ignition delay time is that if I start the process impulsively, in other words, I put a cold material in front of a radiant panel, okay, I know when time equals 0. And then I can wait until all these processes happen, of which I cannot see any of them. I cannot measure any of them. We don't have appropriate diagnostics to be able to actually measure, for example, the migration of fuel within a porous media. We cannot do that. None of these events are observable. But the one thing that I do know is that at some point it will ignite. Is that okay? And the ignition is something that I can see. So I can establish time 0, I can establish time to ignition, which effectively gives me an observable parameter. Okay, something that I can measure. Okay? So the next thing is try to create an equation that describes that observable parameter. So then by comparing my equation that calculates the ignition delay time with my measured ignition delay time, I can extract some of the parameters that I cannot measure. So in a way, what you're doing is an inverse model. You're taking something you can measure, and you are comparing it to an analytical formulation so that you can extract the parameters that you need. Okay? So the simplest possible formulation that I can have is a one-dimensional heat transfer equation. Okay? So how do I get into a heat transfer equation that is one-dimensional? I'm going to make my sample big enough. Okay? I'm going to insulate it well enough so that at least in the observable area, I know I don't have gradients of temperatures in Y and Z, and I only have gradients of temperatures in X. Is that okay? So I'm creating an experiment that fits the model that is the most simple. Okay? So can I do that? Yes. Will there be an error bar? Of course. But I'm going to try my best to make sure that my heat transfer is as one-dimensional as possible. Okay? Now, many people will argue that obviously that assumption is going to break down if the heat flux that you're imposing is very low, because the lower you get your heat flux, the more your heat losses are going to be important. Okay? So normally this formulation works for moderate to high heat fluxes, where effectively you can argue that you have a very strong one-dimensional flow in one direction of heat. Okay? So basically, I am going to try to make it as one-dimensional as possible with x equals 0 at the surface that is being heated and x equals L at the back surface. Now, to simplify the problem, I am not going to vary the heat flux. What I'm going to do is put a radiant panel with a well-characterized heat flux in front of it so that I'm putting a constant supply of heat into the system. Is that okay? Again, I'm creating an experiment that is as simple as I could possibly have it. Is that okay? So, there we go. Constant heat flux, one-dimensional, simplest possible case. So, this is the equation. So, heat conduction in one dimension, the thermal conductivity is a variable of temperature, so it remains within the differential. Specific heat density is the enthalpy changing as a function of time. These are the heat sinks and the heat sources, and this is in-depth radiation. In other words, I cannot assume that all the radiative energy is stuck at the surface. Some of it is going to potentially propagate inwards because the medium is not necessarily completely opaque. So this is the energy conducted. This is the energy generation or the energy sunk if it's pyrolysis. This is in-depth radiation, and this is the energy accumulated or the enthalpy. Okay? Your boundary conditions at time equals 0, T is T ambient. At x equals 0, the heated surface, conduction into the solid at x equals 0 plus is equal to the energy absorbed by radiation minus the heat conducted back to the gas phase minus the surface re-radiation. Is that okay? So this is what is lost by re-radiation, this is what is absorbed, this is what is conducted. Okay? Now, I haven't put a convective heat transfer coefficient. I could actually put a convective heat transfer coefficient, but basically I'm doing conduction back through the gas phase at this point. Okay? Now, in the back, I'm going to have conduction reaching the back has to be equal to some losses at the back. I could, again, represent this in whatever level of complexity that I want, okay? But I'm just going to leave it here at the meantime as a loss. Normally, you have two schools of thought. There are the people that think that if you insulate the back, then you minimize this term and you can make it almost zero. And there's the people that think that there is always going to be a significant error in trying to do that, so you might as well make it a complete heat sink. So a heat sink, if you put a big block of aluminum in the back, by measuring the temperature of the aluminum, you can actually quantify the heat losses. Okay? Either way, it's the same, but effectively you're creating an experiment that is minimizing your error. Okay? So there you go. Now, the big problem is the fuel generation, because to be able to ignite, I need to produce fuel. So the key parameter that I want to obtain is the amount of fuel that I'm being generated. So the amount of fuel that is being generated is going to be given by this expression. Now, what does this expression mean? So you're saying that if this is my solid, okay, and I have a gradient of temperature, I'm not going to assume ahead of time that I have a high activation energy. Okay? What I'm going to assume is that effectively you can produce fuel at every level because the reaction rate is some e to the minus e over RT. Okay? Okay, so if I have a reaction rate, then effectively it's a continuous function. So wherever I am, I will produce mass. Okay? Now, obviously, if I have a very, very high activation energy, most of the mass will be concentrated at the surface. But if the activation energy is slightly slower, then effectively I'm going to produce mass in depth. Now, then if you look at what comes next, then you have this concentration, because effectively these reactions might not produce only fuel. Part of the fuel might be oxidized because you have diffusion going inside. Okay? So this will be 100% or a mass fraction of 1. Okay? So this is the amount of mass that is being produced by the chemical reaction. Part of it might be already fully oxidized. So if I have diffusion of oxygen coming in, not everything that comes out can be fuel. Part of it can actually be already CO2, for example, in which case it will not contribute to your ignition. It will be an inert. So effectively, only a fraction goes out, and that fraction is YF. Is that okay? So it could be, in the case, for example, of very, very heavy charring materials, YF is very close to 0. Okay? While in the case of thermoplastics, you know, where they effectively gas melt and evaporate, this YF is very close to 1. Okay? Now, depending on the material that you have, a fraction of it might be trapped. So if you have PMMA, you will start forming bubbles. And the bubbles are filled up with fuel, and they're not coming out. So you have some other permeability or whatever function that reduces even further the amount of fuel that can come out. Is that okay? So at the end, the fuel that comes out is what is being generated, what is not oxidized, and what is not trapped. Is that clear? Okay? So the equation then, it becomes quite complicated because now you have all these different terms. And the problem is that I need to integrate over the entire depth of the material. So I'm integrating over the entire depth of the material. This is the fraction that gets trapped, or that is not trapped. This is the fraction that is not oxidized, and these are all the chemical reactions that are producing the fuel. Okay? And this is where you start getting lost. Because there's no way you can measure this. There's absolutely no way you can measure this properly. You could measure it at the outside, okay? But then a lot of things might have happened in between, but maybe this one can be quantified. This one is almost impossible to measure, and the chemical kinetics, eventually the sensitivity, the compensation, the whatever, it can create a very, very significant problem, okay? So here we're landing in a situation where all of a sudden we are now getting to the point where this becomes an intractable problem, no matter how simple we've tried to make it. So with the appropriate boundary conditions, you know, I can try to solve this. And this is what people have been trying in these pyrolysis models. So when you look at Thermokin, you look at G-Pyro, all these pyrolysis models, what they're doing is effectively solving, you know, these equations here, okay, with these source terms. Is that okay? So that's what they're trying to do. And they keep playing around with different forms of kinetics. They keep playing around with different forms of oxidation. They keep playing around with different potential permeabilities to try to find as close as possible of a pyrolysis of a mass flux being generated by the fuel. Okay? Now, the two main codes right now are Thermokin, that is Torero in Maryland, and G-Pyro, which is Lottenberger in California. Okay? So once again, East Coast versus West Coast. Okay? And so the two models are fundamentally identical, okay, with the exception of a few nuances, and that are more the product of the perception that the researchers have. But effectively, they are desperately trying to create a mechanism to solve those equations. Okay? So now, this is what they're trying to do. And then eventually, they're trying to bring fuel to the gas phase to try to create a combustion process. And for example, you know, a simplified version of G-Pyro was introduced, you know, by Simo Hostika in FDS. So the CFD model now, once you get the fuel coming out, it feeds a combustion reaction, which is really not a combustion reaction, but is purely a mixture fraction reaction where you don't have combustion, you just have mixing. Is that okay? So, and eventually ignition can be established by means of some sort of critical parameter. Now, this is important, okay? Because here there's a big confusion between the flash point and the fire point. Okay? So, can anybody explain to me what is the difference between the fire point and the flash point? I mean, the definitions are there, but what is conceptually the difference? Yeah.
Difference between like a local energy balance and a global energy balance. So your local energy balance would be when you have ignition, which would be your flash point, and then your fire point is when you can actually sustain a fire that moves throughout space.
You are fundamentally right, okay? But it doesn't help explaining what the problem is. You were going to say something?
Yeah, but I think he said that one of them were a sustained flame and the other one was just there for a short while.
Okay, so that's a physical manifestation.
Yeah.
So the flash point is a flash,
Yeah.
and it cannot stay. That's associated to a global energy balance because effectively it cannot produce enough fuel so that the flame can remain in place. Is that okay? So in a way, the fire point, yes, is you have attained a certain global condition that enables the flame to sustain and remain established. Okay? Now that's a manifestation. While in the case of the flash, you have not attained that global energy balance, but nevertheless you do have you're within the flammability limits. So if you ignite, you can flash. There will be a flame, but that flame cannot maintain itself. Okay? Because the global energy balance is not appropriate. Okay? So I understand that's a manifestation. One flashes, the other one stays constant. It is associated to some form of energy balance. But tell me a bit more. What is the fundamental difference? One of them has to do with the flammability, because effectively it's the moment that you enter the flammable range, because you don't have combustion, so you're premixing. Okay? So you have air and you're bringing fuel in it, and eventually you get to the point where you have a position where you are inside the range of the flammable mixtures. Okay? So yes, the flash point actually does happen within that concept that you have to have at least be in between the lean and the rich flammability limit. Okay? But that is not the fundamental difference between the two of them. Let me take a step back and let you reflect. Okay? If I was to say that the flash point is a measure of ignition, while the fire point is a measure of extinction, would you agree with me? No. So one is a measure of extinction, the fire point, while the other one is a measure of ignition, the flash point.
Okay, extinction in the sense that you do not extinguish.
Yes, so that border, if you are above the fire point, you will not extinguish. If you are below the fire point, you will die because you don't have the global energy balance that you need. Okay? Well, in the other case, I have sufficient molecules of both that it can ignite, but it can keep going. So the fire point is the limit of extinction, while the flash point is the limit of ignition. So if you take Lignan's S curve, okay, the flash point is the ignition branch, while the fire point is the extinction branch. Is that okay? Yes. Okay, so if I have conditions such that I can bring it to ignition, Okay, this is where I get the flash point. Now the manifestation is because I'm producing enough fuel that I can attain a flammable mixture, and I will put a pilot or an ignition source that actually ignites that mixture, or I'll bring it to the right temperature so that that mixture ignites. Nevertheless, I don't have the capacity to maintain a global energy balance in the system, so effectively the flame will, if left in its own means, it will die. Okay? On the other hand, if I come this way, and now I have the right conditions that will keep me burning, okay, I'm going to be in this branch of the curve, and this here will be the fire point. Is that okay? So if you think about it in fundamental terms, flash point and fire point are very different things. Now, why is the fire point an extinction condition? Because effectively what is happening is that at the beginning, you have your e to the minus e over RT. This temperature is still too low, okay? So effectively, the amount of fuel that is being produced is too low. So when it reaches the flame, because it's very little fuel, the flame is stretched. So your strain rate is very high, okay? Too high for that condition, and effectively the temperature of the flame is too low. So while you can induce it because you have enough locally, as soon as it depends on the mass flow that is reaching the flame, this mass flow is not sufficient to maintain the flame in place. So it dies. Then you have to wait for a little while, the mass flow builds up again, you get the right mixture, you ignite it again, and boom, it ignites. Okay? But it cannot rely on the supply of fuel because the supply of fuel is too small to give the right flame temperature. Okay? So effectively, all this is explained in one of the notes that I gave you, but effectively you need to look at the two of them in a very different way. Now, obviously, if I want to simplify the problem, in principle, the flash point is an irrelevant value because effectively it will never sustain a flame. While it is observable, okay, it's irrelevant. What I'm really interested is in going all the way to the fire point where effectively I have a flame that is established on top of the material. Okay, that's the objective. Okay, so normally when you look at data on ignition, you will have, again, that there's quite a bit of confusion because some people will actually establish ignition at the moment of the first flash, and some people will establish ignition at the moment the flame gets established. But conceptually, okay, there are two very different problems that need to be addressed in a very different way. Okay? So we're going to deal with right now with ignition as an observable event, as the fire point. But what you're going to see is when I try to simplify it, effectively what I'm going to end up doing is treating it as the flash point, okay? Which creates a bit of a confusion, okay? So I wanted to make that point because you're going to see what is going to happen next. So this is what happens. So I provide heat and the material starts heating up. Okay, at the beginning, the temperature is too low to gasify anything. So the material is still behaving as an inert. It further heats up until eventually you get to a pyrolysis temperature. So the temperature of the surface starts increasing and eventually you reach that pyrolysis temperature. That pyrolysis temperature is not producing enough fuel to ignite the flame. It has to wait for the temperature to get a little bit higher until you actually get to the flash point temperature. At the point you get to the flash point temperature, you see the fluctuations because the flame is flashing, and then finally you establish the flame, and that's the fire point temperature, and then the temperature goes up. Okay? So basically we're moving along the surface of the material, and the temperature is increasing and passing through the pyrolysis into the flash point, into the fire point. And when you go in depth, you're going to get a temperature gradient that brings you to the inside. Is that okay? So these are the temperatures in depth, while this is the surface temperature as it evolves. Okay? So I have three phenomena. One is the onset of pyrolysis, The other one is when I have enough fuel to get a flammable mixture or get an ignition. And one when I have enough fuel to avoid extinction. In other words, the flame is going to remain. Okay? So, all these numerical solutions, as I said, are there, but we're going to try to simplify them because many of these parameters cannot be modeled correctly. So, how does Quintieri simplify the problem? So basically what he says is, okay, my time to ignition is going to be my time to attain pyrolysis. Once I attain pyrolysis, start producing a flammable mixture, and that flammable mixture eventually will reach the flash point. And that is what he calls the mixing time. Okay? Then he says there is a final time, which is the induction time, which is the jump from the flash point to the fire point, which is effectively when you get a flame that is fully established. Okay? So the 3 times effectively correspond to the total ignition delay time. Now, he is going to conclude that the time to reach pyrolysis is so much greater than the mixing time and is so much greater than the induction time that he can neglect these two and effectively say that the time to ignition is equal to the time to pyrolysis. Yes?
Which is also, I guess, conservative in the context of fire safety.
Of course, because it ignites faster than what it should be. Is that okay? So, in a similar manner, the temperature of pyrolysis, which is not a measurable quantity, but now that temperature becomes the temperature of ignition, which is an observable quantity. Okay? So basically, I've simplified the problem, and by doing that, what he is assuming is that the period that he's interested in is purely the period where the material is fully inert. So if it has not reached pyrolysis at the surface, it would have not reached pyrolysis anywhere else. Okay? So, what happens with my equation then? So if I look at my equation, then this term disappears because it's inert. Is that okay? He's going to make the assumption that most fire materials are opaque, so there's no in-depth absorption of radiation. Okay, that goes away. Then he's going to make it semi-infinite, in other words, thermally thick, and it's so thick that effectively you can assume that your back boundary is going to be infinitely far away. The thermal wave doesn't get to the end of the material before it ignites. Okay? So the boundary condition that was at x equals L now is at x equals infinity, and it's basically T equals to T ambient or a gradient equal to 0. Either way will work. Okay? So then he will say, well, this is too complicated. Let's just make it simple. He linearizes the heat transfer coefficient by adding convection and radiation and adding it into a single heat transfer coefficient. So conduction then becomes equal to a total heat transfer coefficient at the surface. Okay? Yes?
Why would you use like a radiation boundary condition?
Because then the mathematics don't work. You cannot get an analytical solution. That's it. Okay? Because effectively what you're doing,
Like you're going to end up with like a nonlinear.
yeah, so the problem is that if you take the two terms, so you're going to have convective TA minus TB, okay, plus radiation, which would be an emissivity sigma TA to the fourth minus TB to the fourth, okay? Then this term is nonlinear, so effectively complicates completely the Laplace transform that you're going to do to solve that equation, and it just doesn't work. So what he does is he says, well, you get epsilon sigma. He breaks this down into TA squared plus TB squared, TA plus TB, and here is TA minus TB, okay? And he says that all this is an HT, okay? Okay, so there's been a sequel of 100 papers of people trying to prove that right or prove that wrong, and the reality is that actually, if you pick up the right number, it works. Yeah, Because effectively, if you think about it, what happens is that the temperature gets fast very rapidly and then more or less remains almost constant. So making an assumption that at least for this part of the equation, these ones are more or less constant, okay, is not such a bad approximation. Okay, it's just the way it works. But there's no fundamental reason for that. It's just simply the way it works. Okay. So anyway, so you simplify that, and then you assume global properties. So you're not going to solve for the temperature-dependent properties, so you can take them out of the differential equation, which effectively gives you this very simple semi-infinite solid equation to solve. Okay? So the simplified problem then becomes this. Okay? And this is your initial condition. This is your boundary condition at the heated surface. Okay? And this becomes your boundary condition at the back surface. So effectively, then, if you do a Laplace transform of that, then you can get the solution to the equation, and then you simplify it for high heat fluxes and do a Fourier series expansion, and then effectively you get a very simple expression, which is that. Okay? So the solution to the math is Laplace transform followed by a Fourier series expansion, but the Fourier series expansion has to be for times that are very short. In other words, when the heat flux is fairly significant. Okay? There's a different solution for the heat flux that are low. Okay? That will be the same Fourier series expansion, but for a long time. Okay? But let me just use the one for the short time. Okay? So what can I see here then? So what you can see here is effectively the observable event, the time to ignition, the thermal inertia, the ignition temperature, and the externally supplied heat flux. Okay? So you're going to supply a heat flux externally. Okay? That heat flux is going to be put impulsively, and then you're going to establish how long does it take to ignite. And by collecting data on these terms, you're going to extract the thermal inertia and the ignition temperature. Okay? So the material properties become the thermal inertia and the ignition temperature. The inputs are the external heat flux. The observable event is the time to ignition. And obviously the ambient temperature, you will measure it. Okay? So that gives me the ignition, but I still need to be able to work the flame spread out. Okay? But at least I'm going in the right direction. Okay? So the final one is the burning rate. Okay? And in the last hour, I'm going to go back and revisit all this the way the test was created. Okay? What I did here is I just gave you the equation that gives me the information on ignition, so I can find these parameters. Okay, so that then I can plug that into my flame spread equation, and with that I can get the flame spread. But I haven't done it yet. Okay, the final one is the burning rate, and the burning rate generally follows a form like this. So this is a charring material. So effectively the material ignites, and then it has a very high burning rate at the beginning, but eventually starts decaying as the char gets thicker and thicker and thicker until it reaches some form of a steady state or it dies. Okay. And that is a very difficult thing to measure. So basically the way it's done is what people call the cone calorimeter. So what you do is basically take the heat release rate. Okay? You're going to get the same smoke layer as we did before. We're going to measure the amount of air that comes in, which is the same as it comes out. But here it comes in with ambient oxygen, but it leaves with the products of combustion. So effectively you can calculate how much oxygen you have consumed. So this is oxygen in, this is oxygen out. So if you subtract the two, you get the consumption of oxygen. And then if you multiply by the heat of combustion per kilogram of oxygen, you get the heat release rate. Okay? So effectively your heat release rate then becomes your heat of combustion per kilogram of oxygen times the mass of oxygen consumed. Yes?
Sorry, in your mass of gas flow is remaining constant the whole time, even when you have your oxygen reacting?
Yes, because I'm controlling the fan.
Okay.
Okay? So you control the fan, so you know how much mass you're moving through. Okay? And so effectively this is measured. This is measured. Well, this is ambient. And these two have to be the same, conservation of mass. So effectively, that's what you get. So now, if I then take this heat release rate that I have calculated by doing this, and I make it equal to the heat of combustion according to my table, and I divide by this, then I get the burning rate. Is that okay? Yep. So, heat of combustion, complete combustion of per kilogram of oxygen is 13.1, and that's the term that you're going to be using, which effectively gives me the final parameter. Is that okay? Yep. So I can go then back to my equation. Now I have the three of them, and my problem is in principle solved. Okay? So the final hour, what I'm going to do is basically create the experiment. Okay? That effectively is going to give me all the numbers, so I know what the theory is, I know what the assumptions I made, I know more or less what the parameters that I'm looking for. So what I'm going to try to do is basically create the experiment that gives me all that information. Okay? And that is basically due to Quintieri. So Quintieri created the experiment, for that. So again, let's take about maybe 5 minutes, and I am going to grab a coffee, so I'm not answering questions during the break. And so let's break for about 5 minutes.